Okay. Good morning or good afternoon, depending on where in the world you are at this point in time. Welcome to our monthly AI Ready speaker series. I'm delighted today that we have as our featured speaker, Dr. Babak Salimi from University of California, San Diego. He's going to be speaking on certifying fair predictive models in the face of selection bias. I'd like to just introduce him briefly. I'm going to turn it over to Dr. Salimi for this session today. Dr. Salimi is an assistant professor at, and I'm going to mess up the H of the HDSI, but the Data Science Institute at UCSD. Prior to this, he had been a postdoc in computer science and engineering at the University of Washington, where he collaborated with Professor Dan Sushu and the database group there. Dr. Salimi received his PhD from Carleton University School of Computer Science, where he was advised by Professor Leopoldo Bertozzi. His research focuses on responsible data management and causal inference, including algorithmic fairness and transparency. Dr. Salimi has made several significant contributions to the understanding of responsible data management and analysis, including explainability, fairness, reliability, and robustness. Dr. Salimi has a strong interest in database theory and data management. His research achievements have been acknowledged with awards such as the Postdoc Research Award at the University of Washington, the Best Demonstration Paper Award at 2018's VLDB meeting, the Best Paper Award at 2019 SIGMOD, and the Research Highlight Award at 2020 SIGMOD. Please join me in welcoming Dr. Salimi for today's talk.
Awesome. Thank you very much. Thanks for the kind introduction. Let me go ahead and share my screen. Okay. Do you see the slides?
Yes.
Perfect. Hi, everybody. I'm Babak. I'm an assistant professor at HDSI. Today, I'll be talking about our most recent work in the context of algorithmic fairness, specifically how we can ensure an algorithm or machine learning algorithm that we train on top of a training data that suffer from selection bias is going to be certifiably fair under very restrictive, under very limited assumptions. So please stop me if you have any questions. Let's make this interactive. Before getting right into the main sort of part of the talk, let me introduce myself a little bit in the sense of what is my background. I'm coming from a background in data management, and at UCSD, I'm the director of the Responsible Data Management and Analysis Lab. And in our lab, we focus on answering some of the most sort of important and critical questions in data science, namely, how can we ensure that the conclusions and insight that we get out of the data science pipeline are fair, reliable, and valid? How we can ensure that the entire process in the data science pipeline is transparent and explainable, so that our conclusion becomes indisputable. And finally, how can we protect data from various types of data quality issues and biases throughout its life cycle? So during the, is there any comment in the chat? Okay. So over the, in our sort of group, we are focusing on addressing issues related to bias and fairness and robustness, accuracy and reliability in various stages of the data science pipeline. We work on wide ranges of topics, including improving the quality of data and data cleaning methods for machine learning, responsible data management, which focuses on mitigating biases throughout life cycle of data, and developing reliable decision-making system, the transparency, and finally causal inference from complex relational data and multimodal data analysis, and finally explainable AI. During the past 2 years, I've developed several systems, including Goofer and Lewis in the context of explainable AI. The first one generates feature-based explanations for opaque machine learning algorithm that are causal and contrastive, lots of interesting properties. The second one, Goofer, generate explanations for outcome of machine learning algorithms in terms of subset of training data that are responsible for that sort of unexpected behavior. Nexus is a system that integrates a particular data set with external data sets, external open data such as knowledge graphs, open data lakes, and so on and so forth, and searches for potentially confounding variable that explain particular unexpected correlation or sort of observation in data, and Hyper, which is a system for answering hypothetical what-if queries in the context of relational data. Today, I'm going to focus on CRAB, which is a system for training fair models from in the presence of selection bias. Okay, so I'm not sure if I have to convince you that algorithmic fairness is important, but nonetheless, over the past few years, there has been an increasing awareness about the fact that algorithms, despite being objective and evidence-based, they could be highly biased, right? There has been a lot of media attention about algorithms deployed in sensitive domains such as healthcare, finance, and criminal justice systems that were found to be highly biased, which kind of highlights the need for developing fair and unbiased algorithms. But let's discuss very quickly what are the sources of bias, why these machine learning algorithms could end up being biased. And the answer is very simple. They are biased because they could be biased because these algorithms essentially mimics what there is in their training data. And data could reflect existing biases in the real world, suffer from various types of data quality issues that could lead to biased models. Let's go through a bunch of examples. For instance, data may incorporate historical patterns of bias in society. For instance, loan decisions believed to be highly sort of historically biased against certain racial groups. If they collect data from these contexts, the data is going to reflect the existing bias in the real world. Bias may also be due to data collection or sampling methods that inaccurately represent the ground truths. For example, as we're going to discuss later on, in the context of predictive policing, police data is subject to various types of biases, including selection bias, which is a big problem. There are other issues such as adversarial data attacks, for instance, data poisoning attacks, or issues that may arise during the pre-processing pipeline. For instance, when we integrate data in sort of real-world data pipeline from various sources, that could introduce various types of biases. And to make the matter worse, bias is not just the product of data quality issues. Even if we have a sort of perfectly unbiased data without any sort of data quality issues, whatever that means, any sort of decision that we make during designing machine learning algorithms, choice of loss function, the design of, for instance, architecture of the model, and so on and so forth, they could actually introduce bias. Today, I'm going to talk about algorithmic fairness in a very simple context, but the observations and that we make and the solution that we propose goes beyond this simplistic setting. Today, I'm going to focus on fair classification. In this context, we have a very simple mapping from an input space to an output space. For the sake of simplicity, let's assume the output space as a binary. So we're going to make a binary decision, for instance, loan accepted or loan denied. And then we further assume there is a sensitive attribute such as gender, race, and so on and so forth that are associated to the input space, right? And we're going to denote it as S, 1 for protected group and 0 for cleavage. Again, for simplicity, I assume it's binary. It doesn't have to be in general. And then as running example, I use a very simple example in the context of predictive policing. Suppose we collect a data set that include variables such as crime rate, drug use, social cultural traits, and so on and so forth. And the goal is to train a machine learning algorithm to predict crime type. Let's partition the variables in the in terms of Z, W, sensitive attributes, and for instance, zip code. I'm going to use a very simple model in order to kind of show the causal relationship between these variables, because later on I'm going to use it. If you're not familiar with causal inference, it's just a very simple sort of graphical representation of causal relationship between variables. In this graph, nodes represent the attributes in a particular domain, and then we have an edge between them if we believe that they are causally related. So in this case, Y is the training label drug use. It's causally affected by a set of variables that we believe they causally affect drug use, for instance, crime type, And then we also have other variables and the relationship between them. So yeah, they're going to use this as a running example. So of course, if we want to talk about fairness in this context, we need to come up with a computational definition for fairness. There are more than dozens of fairness definitions out there. Today, I'm going to use a very particular definition, but again, the observations that we're going to make, they're generalized to other notions of fairness. I'm going to use conditional statistical parity, which asks for something which is very intuitive and simple. It essentially declares a classifier as fair if the decisions by the classifiers, the output of classifiers, are statistical independent of individual sensitive attributes, once we control for a condition on a set of admissible variables. In the context of our example, it would be the decisions in terms of whether we have a high likelihood of prime use or low likelihood of prime use is independent of individual, for instance, race attribute or gender attribute, once we control for a set of variables that we believe they causally affect prime use. And we refer to them as admissible variables. And then if you are familiar with algorithmic fairness, there are other sort of notions of popular notions of fairness, such as a statistical parity or equal odds, that are sort of particular case of this conditional statistical parity. For instance, if we set the admissible variables as an empty set, which essentially means all variables are inadmissible, then the definition boils down to they should be marginally independent, which is essentially, which recovers a statistical parity, if you're familiar with it. That it says just a positive output of the decision, a positive output of the algorithm should be basically have the same ratio for both sensitive and both protected and privileged group. And if we set the admissible variable to the ground truth training labels, then it recovers equality of odds, which essentially says the ratio of false positive and false negative of the classifier should be the same for both protected group and for privileged group, which is something which is very intuitive. And then if you need a refresher on what do we mean by this conditional sort of independence, it essentially says for all sort of specific estates of the admissible variables or subpopulation with different estates of admissible variables, the positive decisions of the algorithm should be equally distributed for privileged class, and protected class, right? So we want to essentially create some sort of invariance between the decisions made by the algorithm and their sensitive attribute. But like I said, there is no general sort of consensus of how we should define this invariance. This is a particular definition. There are dozens of other definitions out there, but typically you can capture them in terms of a conditional sort of independence between sensitive attributes and outcome of an algorithm, but different sort of choices for variables that we should condition. Okay, so this is going to be our definition for algorithmic fairness. Now the next question is, okay, given an algorithm, how we should measure sort of the degree of violation of an algorithm from this fairness definition. For that, I'm going to use this simple formula, which essentially compares the positive ratio of the decision, the ratio of positive decisions made by the algorithm for the protected group and for the protected group and privileged group in each sort of subpopulation with a particular admissible variable, and simply take the average, right? So if this is 0, if this sort of, I'm going to refer to it as fairness query, and I'm going to denote it as Q of H and omega. I'm going to shortly tell you what do I mean by omega. But if this sort of this equation turns out to be 0, then we declare that the algorithm is fair. Otherwise, we're going to say it's unfair. Okay. Next question is how we should compute this sort of this measure of unfairness. In practice, as you know, we have a training data, which is a sample from some target of population, and then we can compute these probabilities simply by using, for instance, empirical distribution of these variables In this context, for instance, if A, the admissible variables, is a categorical variable, then you can simply go ahead and use a very simple SQL query to compute these proportions. If you have a background in databases, it just computes the proportion of positive decisions of the algorithm based on basically group by the sensitive attributes and group by the admissible variables to compute these proportions and then take the difference between them. What I'm trying to say, it's very simple to measure a degree of unfairness if A is on a categorical variable. Okay, so now we know how to measure algorithmic fairness and quantify to what extent an algorithm violates a definition of algorithmic fairness, in our context, conditional statistical parity. Now the next question is given a fairness definition, how we can train a machine learning algorithm to ensure that the algorithm is going to be fair. And then there are basically three ways to do this, three popular ways to do this. The first one is by performing some sort of intervention in the training data that we use in order to train a machine learning algorithm. Here, the idea is essentially to either reweight data or transform data by changing or perturbing attribute values, or changing sort of covariates or training label in order to sort of remove some sort of unwanted or undesirable correlation that are reflected in the training data, right? For instance, for statistical parity, one popular way is to reweight data in order to make the distribution of covariates or the distribution of features that we use in order to train a machine learning algorithm independent of the sensitive attribute, right? And that's one way we could do this. There are other ways in the context of supervised learning. For instance, we also have in-processing, in which we essentially, if you just, to give you a refresher, in the context of supervised learning, we have a loss function, and the objective is to find a model or a hypothesis that minimizes the empirical loss function that we use the training data to compute. And then in order to ensure that this model or hypothesis is fair, we can sort of subject this optimization problem to a fairness constraint. For instance, we could say the hypothesis that should optimize, that should minimize this loss should also satisfy this fairness constraints. For instance, in our context, the fairness query, that simple formula that I showed earlier, should be evaluated to less than epsilon. In that case, we're going to say the algorithm is epsilon fair, okay? So we can do in-processing, in which, like I said, we enforce the fairness as a constraint or a regularizer in order to basically ensure that the machine learning algorithm that we train using a training data is going to be fair. We can also do post-processing. That's another sort of popular method in order to sort of train a fair machine learning algorithm that I'm not a big fan, because during sort of, you need to have access to people's or individuals' protected attributes during the inference, which is not always the case. Okay. All the existing sort of techniques out there, or majority of the existing techniques out there, they rely on a critical assumption that I want to argue it fails in general. There are more than dozens of fairness packages or tools out there that you could use in order to train fair model. And all of them, they rely on the following assumption. They assume the distribution of training data that we essentially have a sample of, right, is the same as the target distribution, right? The distribution, I denote the distribution of training data, the distribution which is represented by the training data as delta, and I sort of refer to the target distribution as omega. This is the target distribution is essentially the distribution that you want to deploy a machine learning algorithm to, right? So all of them, they assume these two are the same, or and then they use pre-processing, in-processing, or post-processing in order to enforce that constraint. But I argue that in general, almost all the time, training data suffer from data quality issues, such as selection bias, which is going to be the focus of our talk today, systematic data errors, technical biases that may introduce during a pre-processing data or data collection or data integration, measurement error, missing data. And in the presence of all of these data quality issues, the training data is not representative of the target population. And you may say, okay, we can use data cleaning techniques that are out there, data debiasing techniques that are out there in order to deal with this. But the caveat is, what you get out of data cleaning is essentially maximum likelihood data, which is sort of consistent with the available information. And then there is not a unique solution to the sort of maximum likelihood problem in general, in the sense that what you get out of data cleaning is one data set, which kind of has some good properties, but there are other sort of data sets that you could imagine that have the same properties at the same time. In other words, the distribution of the ground truth data is not identifiable in general. In that case, whatever we get out of data debasing and data cleaning in general, it doesn't have guarantee that we get sort of desired properties during inference. In the context of our discussion, all these sort of fair ML models, all these techniques that are out there in order to train machine learning algorithms that are fair, they fail to produce a fair model on the target population due to data quality issues. We showed this empirically in a Sigma 2022 paper. By introducing a little bit of data quality issues, then you will get a situation in which you get a model which is accurate and fair during training and testing, but if you deploy it on the target population, you get something which could be highly inaccurate and highly biased, or even decently accurate but highly biased at production, and you cannot detect this without further assumption and further information just during training. What happens, for instance, in the context of fairness is, so our training data suffers from data quality issues. And in the presence of data quality issues, the distribution of training data, even after you apply your data pre-processing, apply algorithms to deal with missing data and so on and so forth, or measurement error, or and so on and so forth, it's not necessarily representative of the target population. There's a mismatch between the training distribution and the target distribution. And then what happens is that simple sort of fairness query that I discussed earlier, it measures something that doesn't generalize, right? What does it mean? Is that, for instance, we may sort of train a machine learning algorithm which is completely fair, which means this fairness query evaluates to 0 on the training data. But when you deploy it on the target population, and if you have your hand eventually to a sort of unbiased and representative sample of a target population, now all of a sudden you get a model which is highly biased, and vice versa, right? Today, like I said, I'm going to focus on selection bias, not all data quality issues in general. Just to refresh your mind, let me tell you what selection bias is. Selection bias occurs essentially when the data that we use for training machine learning algorithm for hypothesis and statistical inference in general is not collected at random, right? It's collected in a non-random manner, leading to a data set that is not representative of target population. This has nothing to do with controlled experiments. Here, we are essentially saying that in general, the independence assumption in IID assumption, it fails to hold in general. Why we may have this issue in practice? It can be caused by various factors, including cost and feasibility of data collection, historical discrimination, and individual biases. And then in the context of, in particular, healthcare, finance, and predictive policing, this is a major obstacle in order to create models that are accurate, fair in practice. To convince you more about selection bias, let me discuss how they incarnate themselves in the context of healthcare, predictive modeling, and finance, because these are sort of very sensitive domains and sensitive and important domains. In the context of healthcare, you may confirm that studies are often conducted on data collected from individuals who have already been admitted to hospitals, right? In the context of COVID, for instance, the existing available COVID data sets, they're collected from individuals who have been either tested positive for COVID or they have been hospitalized, right? And that's selection bias right there. There are many people that are contracted with this virus in practice, and we don't collect any data on. And this is a missing data issue, as I'm going to discuss shortly. It's a selection bias situation. In the context of predictive policing, data is, we only have access to data collected by the police departments. And it is believed that this data is highly biased because of the bias of the police officers. Or if you also think about it, certain neighborhoods or zip codes are patrolled more than others by police department, which is another sort of source of selection bias. So we believe in general it's highly biased. Also in the context of finance, data collected from financial institutions that are being used for training machine learning algorithm for credit risk assessment and loan approvals are highly biased in general. So there's a question in the chat box. Can you please elaborate why non-randomly collected data leads to data issues? Sure, I have a numerical example that elaborates on that issue. But to give you a short answer to your question, what happens is when we have non-randomly collected data, we're going to end up with a data set in which some of the statistical properties presented by that data set are distorted. They do not generalize due to sort of missing data issues as a result of this selection bias. For instance, at UC at San Diego, you want to estimate the average income of people, and then you only collect sort of data points from La Jolla, right? So the estimate that you obtain by simply sort of computing average income of your sample data is going to be highly biased, right? Because of the obvious reasons. But I'm going to get back to this with a numerical example. Yeah, in the context of finance, we have this issue. It's a severe issue when we use the data collected by existing organization in order to build tools for risk assessments, because we know that individuals from certain racial or social economic backgrounds may have less access to financial services and have a chance to build credit history, which is again another example of selection bias. There's also this interesting read that I sort of recommend to gain more sort of insight on how selection bias in general may affect the reliability of any sort of type of analysis, not just machine learning, it could be hypothesis testing. So this this paper looks into the impact of collider bias, which is another sort of fancy term for selection bias, if you're not familiar with this domain, in the context of COVID studies. There are lots of interesting examples of why restricting ourselves to data that are collected from hospitals could lead to all these sort of funny conclusions, a lot of false discoveries, exactly because of the selection bias in data. Yeah, let me now show you a numerical example in the context of a running example. Remember that we wanted to train a machine learning algorithm to predict crime rate, and then we collect a bunch of data points and record information about their crime type, age, race, zip code, and of course the training label, as well as other sort of attributes. In an ideal world, what we're going to do, we're going to take a random sample. By random sample, the decision for collecting a data point should be a result of a random process. You toss a coin, and then you're going to select a data point, or you do not select a data point. In an ideal world, if we have a random sample, then we can go ahead and use that sample in order to train a machine learning algorithm. And then we would not run to any of the issues that we have discussed. In this context, if you check, this is on the right-hand side of the slides, I have a contingency that shows the interaction between age and the training label. And as you see in this simple sample, if you think about this contingency table, age is not correlated with the training label, right? So in this case, if you train a machine learning algorithm, it does not pick up age as a predictive attribute, right? It's not a predictive feature. But like I said, in the context of this example, we do not have access to an unbiased sample. We have a sample which is collected by police departments, and then the selection of data points into the sample depends on individuals' attributes. For instance, it could depend on their zip codes, because like I said, some zip codes are patched more than others, and social cultural traits of individuals that sort of affect police officers in order to essentially decide whether they want to take this as a sample or they do not. In this context, I'm going to use a variable C to show that whether police department select these data points or not, right? when 1 shows that a particular data point is selected and 0 shows that they are not selected. The observed data, which is collected by the police department, could be seen as a subset of that representative sample, right? We have missing data issues. All those tuples for which C is equal to 0 are not selected by the police departments because, like I said, certain zip codes are more patrolled than others, so it's a higher chance that we have more data points or sample from that particular neighborhood. So what happens is the following. Now, if you consider the same contingency table to look into the interaction between age and training label, you get the second contingency table, the one below. And now, all of a sudden, in the selected subset of data, we see a huge correlation between age and the training label, right? What I mean by that is, in the real world, if you had a non-random, you have a fully random sample with a representative sample of the population, there were no correlation between age and training label, which means in the real world, just for the sake of assumption here, assume there is no sort of legit correlation or true signal between them. But all of a sudden, the fact that the data is non-randomly collected creates a spurious correlation between age and the training label, which exists in the training data, but does not exist in the target population. And what happens is, if now we use this sort of the highlighted part in red to train a machine learning algorithm, we end up with an algorithm. We may end up with an algorithm which is perfectly fair, which is which does not pick up age as the predictive feature, which picks up age as a predictive feature, where we know that in general it's not predictive, right? It could be an algorithm which is very accurate, but during training and testing, but highly inaccurate when we deploy it in the target population. I'm not sure if all of you have background in graphical models, but there's another way to explain this phenomenon, which has to do with the collider bias that we observed in the title of that COVID paper. What happens could be explained as follows. So remember this graphical model that shows the causal relationship. It's a simple graph that shows causal relationship between the attributes or variables in our domain. What happens is we can graphically capture this selection bias by adding a node to these graphs. The node is C, and then connect it to all variables that affect collection of data. For instance, the context of predictive policing, we assumed the selection of data point depends on individual zip code and their social cultural trait. So I'm going to add two edges from Z to C and zip code to C. And then you can think about the observed data as a sample from a conditional probability in which C is equal to 1. In other words, we always take sample from a subset for which C is evaluated to 1, right? We are essentially sampling from a conditional probability. And then, like I said, if you're kind of familiar with graphical models, what happens is the result of conditioning on that C creates a spurious correlations, for instance, in this case, between race and age and the training label, which means we have a sort of correlation that is reflected. It could be very strong correlation. This is not something that you can capture with p-value and a statistical significance, because it's going to be a correlation between race and age that absolutely statistically significant on the training data. But what happens is this correlation is fake, it is spurious, it does not exist, it does not belong to the target population. And why is that so? This phenomenon is called as collider bias, or explain-away effect, and happens when we condition on the common cause of two effects, right? For instance, in this case, race and age, they're basically independent. But when we sort of condition on that collider, we are going to induce a spurious correlation between them. And if you're not familiar with this sort of paradox, another way to refer to this is Brexton paradox. So what happens if you have X, Y, and Z, and then X, Y are independent, but Z is a function of both of them. If we condition on Z, if we know Z, right, and one of the inputs, if we know X and Z, then that would gives us information about Y. So that's why we have this spurious correlation. Again, if you're not familiar with it, but you're interested, look up for collider bias, explain away effect or Brexton paradox. And that's exactly what happens when we have selection bias, because the selection process, it depends on individuals' attributes. We condition on the selection process, and the selection process creates all these sort of spurious correlations that exist in the training data, but do not generalize to the target population. Okay, like I said, what happens here is if we use the highlighted subset of data to train a machine learning algorithm, we could get a perfectly accurate model during training, but that model, this is a simple model that I have in the right-hand side, is a simple decision, let's say decision tree, bunch of if then else rules that perfectly classify the training label in the training data, but when we apply to the entire sort of population, we get a model which is completely inaccurate, which is completely garbage, and then it's going to be highly biased because now it depends on, it highly correlated with individuals, for instance, age and race. Okay, I hope I was able to sort of convince you that selection bias is very detrimental when it comes to machine learning model and beyond. Okay, of course, I was not the first one who came up with this issue. There has been a lot of work in the context of machine learning and beyond that look into how we can deal with selection bias in general. But all existing models, they rely on very restrictive assumptions. And let me explain what are those assumptions. Almost all of them, they rely on the assumptions that we do have access to unbiased sample from the target population. So they assume that we have a large training data which suffer from selection bias, and then we do have access to a small but unbiased sample of a target population, right? And they essentially use this data in order to, for instance, reweight the biased training data in order to compensate for selection bias. For instance, you can estimate a propensity score or the propensity for selecting data points, and then reweight based on propensity score to compensate for that bias. By the way, this is very much related to domain adaptation and covariate shift, but let's not get into that discussion. But here's the thing: obtaining unbiased sample from a sort of particular domain that we are interested in general is just impossible. For instance, the context of COVID, it's just virtually impossible to get our hand to a data set which is completely unbiased. In the context of predictive policing, in the context of also finance, it's almost impossible to get our hand to an unbiased sample. Okay, that's the first caveat. And the second one is the problem is very complex from the technical perspective, meaning that even if we have that unbiased sample, in theory, we can sort of debias data by reweighting it, but then you need to have access to accurate weights. And for essentially estimating those weights accurately, you need a lot of data, right? You need a lot of data. Like I said, it depends on, the biasing depends on either having an accurate model of the propensity score, or you need to do density ratio estimation. And if you have high dimensional data, they have a very poor finite sample properties, and they do not generalize very well. As I'm going to hopefully get the time to show you some experiments, they perform very poor in practice. Okay, this essentially motivated this work in which we are going to discuss how we can train machine learning algorithms that are certifiably fair, 100% guaranteed they're fair, and then we assume we don't have access to unbiased data, right? We sort of we get rid of that restrictive assumption, no access to unbiased sample from the target population, but we assume we have background knowledge about how data is collected. We know the provenance of data collection, right? For instance, we assume in the context of police data, it's fair to assume the data collection depends on individuals' residential information and their social cultural traits, okay? That's the only assumption that we're going to make. And I would argue that in many cases, we do have that background knowledge and information, and those knowledge, they don't have to be perfect in order for our system to work. And then we essentially use insight from databases and say, essentially enforcing fairness in the context of machine learning algorithm could be seen as some sort of inference or query answering from inconsistent and incomplete data. What do I mean by that? Let me skip this because this is technical for database folks. Let me explain the insight, the gist of idea here in our case. So the input to our problem is a machine learning model, a fairness query, which measures to what extent a particular model H is unfair in the target population, because that's what matters. And then we have a bias data, for instance, bias police data. In addition to that, we assume we have access to background knowledge about the provenance of data collection. And we use the language of causal inference in order to capture that information. I explained this data collection diagram, which is a fancy name for causal model, augmented with this node C that shows selection of data points is a function of individual zip code and the social cultural traits, right? So I encode the assumptions about data collection provenance or data collection process using this graph. It's not critical to our discussion. And then we say, okay, in the presence of the selection bias, there is no way that we can, in general, debias the data, which means to transform or reweight this data to another data set, which can say 100% guarantee it should representative of target population. But what we could do is the following, and this is the sort of insight that comes from databases. We can assume, we can come up with all possible ways that we could complete this incomplete data. Because another way to think about selection bias is we have incomplete data, right? In the context of COVID, we don't have information about all sort of individuals that if we include them to the data, all of a sudden data becomes a representative of target population, right? But we can conceptually consider those data sets, right? Those data sets that can be obtained by completing all these incomplete data, such that all these data sets, all these sort of possible data sets, which I'm going to refer to them as a repair of the original bias data, are consistent with the available information, which means they're consistent with whatever part of the bias police data which we believe it contains reliable information. I'm going to touch upon that shortly. And then information that are encoded in the causal diagram. We conceptualize all of these possible words that are compatible with the existing information, and then conceptually we compute that fairness query on all of these possible words. And here is the important part. Since we assume all possible words, one of these words, at least one of these words, is representative of the target population. We can assume one of these words is exactly what we want. We don't know which word because we don't have enough information. But using our partial information, we can assume all these possible repairs such that one of these data sets is the exact one, is the one that we're looking for. And now if we conceptually, again, compute this fairness query, if we measure unfairness of a model on each of these possible words, then what we could do, we can establish a lower bound and upper bound on fairness of the model, right? And here's essentially what we get. We essentially come up with a bound on fairness of a model, such that it is guaranteed that, again, by fairness query, just to refresh your mind, it's just a number, and the lower the number, the better. If it is 0, then they're completely fair. And what we are doing here, conceptually, we are essentially arguing that we can consider all these possible words and then compute a range for a particular fairness query, such that the true value of the unfairness of a model fall within that range. This is the first sort of insight. The second insight is, it is true that we do not have access to an unbiased sample of a target population. Again, in the context of COVID, it's impossible to have an unbiased sample of the target population. However, we do have access to, for instance, census data, open data sets, knowledge graphs, all these sort of open data sources out there, external data sources out there, that may give us reliable information about the target population. in the context of a running example, for instance, using census data, for instance, we may get a reliable information about distribution of age or race for different zip codes, right? You essentially have information about probability distribution of race and age condition on zip code. And then the thing is, we could leverage this information in order to improve these sort of fairness bounds, right? Because what happens is it restricts the space of all possible repairs. But the major question now is, how can we compute this bound, right? Because if you think about it, for continuous data, the space of all possible repairs, they're infinite. For finite data, it's exponential. And we cannot materialize these repairs, right? We cannot sort of go through all possible repairs, compute this fairness square, and establish bound. It's a difficult problem. Like I said, the information about data collection process and external data sources limit the space of possible repairs. But nonetheless, characterizing the space of all possible repairs is very challenging. It's exponential space. So that computing this lower bound and upper bound is a difficult task. However, we showed that for this particular fairness square that we're interested in the context of algorithmic fairness, what we could do, we can establish closed form formulas for the lower bound and the upper bound that basically solve our problem. But before getting into that part, I want to give you an insight about why collecting information about the provenance of data collection is important. Right now we're discussing selection bias, but like I said, the insights generalizes to other sort of data quality issues. And the takeaway from what we're discussing today is, if we do not collect enough metadata and enough information during data collection, then there is no magic that could save us later on from various data quality issues that may arise due to data collection. We need to collect enough metadata. And if we collect these metadata, in certain cases, they may help us to basically recover the ground truths. I know that we need a lot of strong assumptions to be able to do that, but if not, we can again consider the space of all possible words and sort of do some sort of sensitivity analysis. I think this is a more familiar term to you. Do some sort of sensitivity analysis. Sensitivity analysis is a particular case of what I just discussed. We consider all possible sort of distributions or data sets that are compatible with the available information, and we could establish bounds. Okay, so let's discuss why this sort of external, this metadata could be helpful in general in the context of selection bias. What happens is this graph on the left-hand side that contains information about a data collection process includes a bunch of conditional independence statements. For instance, in this case, we know that zip code and the selection process C, right? The selection process is independent of everything else, all the other attributes, once we know individual zip code and their social cultural traits, right? It essentially include these constraints, and the ramification of this constraint is certain statistics. Sorry. Certain statistics in the bias data. So we started with a data set which is biased. But certain statistics, there are certain statistics in the target population that you could use the bias data in order to compute, which essentially means your data, even though it's biased, it's not completely garbage, right? There are certain statistics that boost the bias data and the target population they agreed upon, right? So it's not entirely garbage. And knowing this metadata about data collection process gives you the ability to identify those statistics and those subsets. So we assume we have this background information, and then the next question is how we can leverage from it and to compute the lower bound and upper bound of fairness. And the answer to that question is very simple. We use, I mean, it's a bunch of math, but what we're doing is we want to essentially compute an upper bound on and a lower bound on this fairness query. And then what in order to do that, we just need to maximize the first term and minimize the second term, for instance, for establishing upper bound and the other way around for lower bound. So the information that we encode in the causal model essentially enable us to decompose these proportions into parts that can be computed from unbiased data and other parts that are unknown, or we need external information in order to compute. Bunch of statistics, right? And then using a bunch of simple sort of math tricks, you can get rid of these unknown parts and essentially compute an upper bound, right? By getting rid of them, you can just assume extreme sort of numbers for them in order to obtain upper bounds, and similarly lower bound. Interestingly, you can basically also incorporate any level of background knowledge that you have. For instance, all the statistics that you could compute from census data for a target population that you want to deploy your model, we could actually incorporate in the sense that we can sort of establish more complex bounds that also leverages from this external information. It's just a bunch of math that shows how we can compute this consistent lower bound and consistent upper bound. Now let me close the loop. How can we use this lower bound and upper bound to train a model which is going to be fair in the target population? And the answer is very simple. So, for instance, if we want to do in-processing, what we could do instead of using the original fairness query as a constraint or a regularizer, we can actually use the consistent upper bound or upper bound on it as a constraint or regularizer. And what happens is the following: you're essentially training a model which is going to be fair in all possible words that are compatible with the available information. So, of course, as a byproduct, it's going to be fair on the word that you want to deploy the model, right? You can think about this again as doing some sort of sensitivity analysis, find the worst case value for fairness of the query, regularize your model with respect to that value, so your model is going to be fair on all possible words, right? And of course, on that particular possible words that you deploy the model. So therefore, it's going to be certifiably fair no matter what. How much time do I have? Can I share some experiments, or should we jump to the conclusion?
You have about 5 minutes left. And I know you said you had a hard stop for teaching a class too.
Yeah, let me share just one experiment because there are some interesting insight that we can get from the experiments. For the experiments, I use 3 data sets: HMDA, law data sets, UCI, adult census income. HMDA contains mortgage applications data to predict loan approval or denial. Law school data contains law school student data to predict exam outcome. And then UCI is a data set for predicting whether individual received high income or low income, okay? And then I'm going to compare with a bunch of fair ML models, pre-processing algorithms, and in-processing algorithms. And 2 algorithms that are actually designed to deal with selection bias. Inverse propensity score-based reweighting, which assumes access to an unbiased data, and then, like I said, reweights the data to compensate for the selection bias. And then it's a ICML paper that formulates the problem using a min-max optimization problem and use an alternating algorithm in order to solve it. Let me share some results in the context of adult data first. So the graph shows a statistical parity versus F1 score of a model. A statistical parity shows whether a model is fair or not, according to basically the definition of statistical parity is just marginal independence between outcome of a machine learning model and the sensitive attributes. And F1 score shows the performance of a model, the higher the better. Statistical parity, the lower the better. F1 score, the higher the better. So for each of these graphs, if a model is in the bottom right of the graph, the better that model. The green region shows the region in which the model is completely fair, or approximately fair, sorry. But the blue dot shows the F1 score and bias of a model trained on biased data. And the red cross shows the bias and F1 score of a model trained on the original data. And this is the semi-synthetic data in which we introduce selection bias ourselves because we wanted to have the ground truths to be able to compare with. And coming up with the benchmark in this context is difficult. So we had to kind of use the semi-synthetic data in which we inject selection bias, which means we remove some of the data points in a non-random fashion. First insight, if you check out the graph on the right-hand side, introducing selection bias leads to dropping only 1% of accuracy, but 5% of discrimination, right? It essentially means if you, in practice, even in the presence of selection bias, we may end up with an algorithm which is pretty accurate, right? Which is pretty decent when we deploy it in compared to their ground truth best model. But it could be highly biased, right? It could be highly biased. And then we compare against, CRAB is our model, which doesn't use any external information. And these are our models that use external information, as I discussed. These are just a bunch of statistics that I'm not going to go through the details. And as you see here in both of these graphs, all these baselines are these fair ML models. They end up with a model which is pretty accurate, but completely unfair. If you check them out, they're completely unfair. Again, they are fair during testing and training, but if you compare them against the ground truth sort of unbiased test data, then they're going to be highly biased. Interestingly, the Quartas model, which is propensity score, which uses propensity score reweighting, and uses an unbiased sample of the sort of target population, because here we have access to that. It leads to a model which is still unfair, which kind of shows that these models, these existing techniques out there in machine learning for training models in the presence of selection bias, they don't work very well because, like I said, it's a very complex problem in general, and the existing methods, they don't have a sort of good finite sample property. So, but as you see in all of these, in both of these cases, our methods, they fall into the green region. We were able to successfully train a model which is certifiably fair by, for instance, here dropping 1% of accuracy, but delivering a model which is completely fair. Using other data sets, we basically make the same conclusions here. For instance, in synthetic data, this is interesting because if you think about it, again, the red cross, the original bias data, it has a sort of 96% accuracy. And then when we introduce data selection bias, we get to a model which has 88% accuracy, so it drops the accuracy quite a lot and becomes highly biased. Here, the original sort of model were completely unbiased. So selection bias drops accuracy and increases a lot of unfairness. But interestingly, once we use CRAB in order to train a model which is now fair, using basically that upper bound and lower bound trick, we end up with a model which is completely fair and much more accurate. So it kind of means this trade-off between accuracy and fairness that you often hear about in the context of machine learning is just a miss. If you address the root causes of bias in the correct way, there might be situations in which you basically improve accuracy and bias simultaneously. And we also have use cases in which we basically use the census data in order to see whether sort of this idea would work in practice, and we are surprisingly it works very well, even we know that, for instance, census data is imperfect in general. So with that, let me conclude here. We discussed data quality issues can substantially affect fairness in machine learning. The effect could be more than fairness. Right now, I have several ongoing projects that looks into how we can propagate this uncertainty due to data quality issues to decisions by the machine learning algorithm, to the actual predictions. It's a very difficult problem to propagate this uncertainty because the process that we use in order to train machine learning algorithm, gradient descent is an iterative process, and coming up with the way in order to upper bound and lower bound the gradients in each step, and then finally propagate this uncertainty to coefficients of to parameters of a model is a difficult task that we are currently undertaking. Traditional fair ML models struggle to address bias stemming from data quality issues. And in real-world scenarios, training data is almost always biased. It almost always suffers from data quality issues. And using existing data debiasing and data cleaning algorithm, it's insufficient. There is no guarantee when we use them that we recover a ground truth representative sample. And using techniques from domain adaptations and so on and so forth, they work under very sort of strict assumptions. And we have outlined an approach inspired by data management to learn models that are certified by FAIR from data by, again, considering the space of all possible words and using essentially the possible words in order to reason about fairness in general. Thank you very much. I'll be happy to take questions. There's a question in the chat box. Let me see if I can address that. Could this fairness evaluation of the data be leveraged for use in data sharing with differential privacy? I'm not sure if I entirely follow the question. If you're still in the room, can you elaborate on that?
I do not think Heidi is any longer here. I'm not seeing.
I went over time. That's why.
Yeah. Yep. Well, if there are, I was going to announce this earlier, just in case we cut it close. If there are any burning questions, maybe I can pass around your contact information and we can reach out. That's okay.
Absolutely.
Okay.
Yeah. Thank you very much, folks.
Thank you so much. You have a good day.
Thank you. Have a good day.
Bye-bye.